For this problem, we have an object that's balanced here, so we're ultimately going to be thinking about the fact that the sum of the torques must add up to 0. Before I start doing that, I'm first going to identify all the forces and ultimately torques acting on this balanced object. So we have a bar here that has a mass of 2 kilograms and is 80 centimeters long, so we're going to have a force of gravity acting on that object itself. We're also going to have the force of gravity acting where there's this 500-gram mass here. We are treating this whole thing as a system here, so I'm not going to worry about the fact that there's a rope connecting it. I'm just going to call it the force of gravity. So that means we're going to have a torque from object 1 and a torque from object 2, both going in the clockwise direction. We therefore need to have some counterclockwise torque, and that comes from this pin. This pin is going to be exerting a counterclockwise torque, and that's what we're ultimately solving for. When we go to set up our problem here, it's going to end up being the torque from the pin minus torque 1 minus torque 2 equals 0. Torque from the pin is what we're solving for here, and then we can fill in RF sine theta for these other two torques from the two forces of gravity that are acting on our system here. So for the first object, it's going to be a radius that acts in the middle here, so 40 centimeters or 0.4 meters. Okay, that's the distance from the pivot here to where that force acts. Okay, because this left side where the pin is going to be our pivot, times the force, which is just going to be the force of gravity. So 2 times 9.8. And then the angle there is 90 degrees because it's just acting straight down, minus our other force, that acts the full length, so 80 centimeters or 0.8 meters, times the force, which is the force of gravity, so 500 grams or 0.5 kilograms, times 9.8 because it's the force of gravity, times sine of 90, and that equals 0. And when we go ahead and solve for this, the sine of 90s obviously go away, they're just 1. We find that the torque that the pin must provide is 11.76 Newton meters. When we round that to 2 sig figs, it just becomes 12 Newton meters. One quick point here, I know the pivot is on the left end here, and the pin acts on the left end as well, but we see that the pin actually goes into the board a little bit. We've talked about how a force on the pivot can't exert a torque, but this doesn't exactly act on the pivot itself. It acts around the pivot, but having that pin go some distance into the board allows it to exert a torque even though it's near the pivot. For this one, we are trying to make this beam balanced here, so this is another sum of the torques equals 0 situation since we have equilibrium, since we're not accelerating. So we're going to start here by thinking about where our pivot is, and I'm going to put the pivot right there on that left end where we have some force from the wall that we don't know and we don't care about. And then I'm going to think about what forces we have providing a torque. So we have the force of gravity, okay, acting on the beam itself, and we have the force of tension holding it up. And then there's going to be some normal force right around here. Doesn't exactly matter which way it acts because there's no torque created by that. The force of gravity on the beam is going to create a clockwise torque. The force of tension is going to create a counterclockwise torque. And so those are the two torques that we need to balance in our system here. So going back to our equation, it's going to be the torque from tension minus the torque from gravity acting on the beam itself is equal to 0. We can substitute in RF sine of theta for each one of those. Okay, and then we can plug in the things that we know. So we know that the radius here for the tension is just going to be 1 times that force of tension times sine of 30 minus the radius for the force of gravity. That's half the length of the beam because gravity acts in the middle there, so 0.5 times the force of gravity acting on the beam, which is just going to be its mass times 9.8 times sine of 90. I'm just going to drop that term because it's just 1. We see here that it would be a 90-degree angle, and that's what we're left with. So we end up getting that Ft times sine of 30 minus 147 is going to be equal to 0. And when we solve for our force of tension, then we get a force of tension of 294 newtons When we round to 2 sig figs, it just becomes 290 newtons. We have another equilibrium problem here, so we know that we're ultimately going to do sum of the torques equals 0. Start with that, but first let's identify all the forces we have. So we have the force of gravity here acting on the diver. I'll call that Fg1. In this case, the board itself has a force of gravity, so I'm going to add that one in, Fg2 there, force of gravity acting on the springboard. And then we have two supports, okay? So this one support here, I'll call this F1, is going to exert a force up. We're also going to have a force here from support 2 on the left side. And we'll think in a second about which way that force is going. We ultimately want to find the magnitude of the vertical force exerted by the hinge, okay, which is going to be this force over here. So when we think about where our pivot's going to be, we don't actually want to put it over here, because if we put it over here, then this force creates no torque. So we keep in mind that our pivot can actually be anywhere, and we're going to place it where there's an unknown force that we don't care about. And in this situation, that right there is the unknown force that we do not care about. We don't care about F1. We know Fg2. We could solve for it, I should say, but we don't really care about that one either. We don't need to necessarily know it. So this is a great choice for our pivot. So with that point, that middle point as our pivot, we have a clockwise torque here from the force of gravity acting on the diver, Fg1. So we need a counterclockwise torque to balance that out. And what that ultimately means is Fg2 actually must be acting down. Okay, we need to push down on the board on that left end to create this counterclockwise torque, okay, that balances the force of gravity. If we pushed up on it, it would create a clockwise torque like that, and it would not balance out that other force of gravity. So now we can go ahead and set up our sum of the torques equals I alpha. So we're going to have torque 2 going the counterclockwise direction minus torque 1 equals 0. All right, and so we'll say RF sine theta for force 2 minus R times Fg1, force of gravity 1, sine of theta equals 0. And we can substitute in the things we know. So F2 acts at a distance of 1.5 meters from our pivot, because that's going to be our R value right along here. We know that the force, that's what we're looking for, and the angle here is going to be 90, minus the radius for gravity, which is this, which also happens to be 1.5 meters because our pivot's directly in the middle. And our force of gravity is going to be 59 times 9.8 times sine of 90, and so that all is going to be equal to 0 here. So what we end up getting then, the sine of 90s obviously go away, and so we get 1.5 F2 minus 867.3 equals 0, which means that F2 is going to be equal to 578 newtons. We want to round this to 2 sig figs, so that just becomes 580 newtons. For this next one, we want to figure out this distance d here that will allow this system to balance. And so we could go ahead and think about our torques, but there's actually a much easier way, since in this case we're only looking for where the system will balance. We can actually think about our center of mass, because we know that that system will balance when the pivot, this fulcrum, is located on top of the center of mass. All right. So in order to do that, I'm going to say this left side here is my x equals 0 point, and I'm going to think about the location of the two objects in my system, the two boards. All right. So the one board, it's 2 meters long, 1 kilogram. Its location is just going to be in its center. That's where it's located. It extends obviously for the whole length, but the center of mass of this board itself is in the middle, and so that's where we're going to use for our center of mass of our system calculation. All right. We also have this other board here, and that is also going to be located in its middle, which is going to be 1.5 meters from the left end, and this one's going to be 1 meter. All right. So now we can go ahead and fill in our calculations here. So this position for object 1 is 1 meter. Its mass is 1 kilogram. All right, so I'm saying this long board is object 1. And then for the second object, all right, its position is 1.5 meters, all right, and its mass is 4 kilograms, divided by our total mass, which is 5 kilograms, and we find that our x center of mass is going to be 1.4 meters. All right, so 1.4 meters from the left end is our x center of mass, which means, all right, that that distance d, where that fulcrum needs to be placed in order to balance our system, is just 1.4 meters. For this problem, we have a flywheel, which is just a giant rotating disc that's used for a lot of different purposes, but one thing it can do is store energy in the form of rotational kinetic energy. And we want to know if the flywheel stores 4.8 megajoules of energy while rotating at 17,000 revolutions per minute. What is the moment of inertia? So what we're thinking about here is that rotational kinetic energy is given by 1/2 I omega squared. Right? So we know that our rotational kinetic energy is 4.8 megajoules, and that mega prefix just stands for 10 to the 6. So I'm just going to say 4.8 times 10 to the 6 joules, because mega is 1 times 10 to the 6th. And that's going to be equal to 1/2 times my moment of inertia, which is what I'm looking for, times my angular speed. However, my angular speed is in revolutions per minute, and we usually have it in radians per second. So I'm going to go ahead and convert this revolutions per minute into radians per second. We know 1 revolution is 2 pi radians. We know that 1 minute is 60 seconds. And so we end up getting that speed is actually 1,780 radians per second. So I'm going to plug that in here, 1,780, and we're going to square that. We go ahead and we solve for our moment of inertia from that, and I end up getting 3.03 kilogram meters squared. If we're rounding this to just 2 sig figs, it's just going to be 3.0. All right, for this next one, we have a sphere with a mass of 120 kilograms and a radius of 1.7 meters, starts from rest, and rolls without slipping down an inclined plane that has a vertical height here of 5.3 meters. And we want to know what is its angular speed at the bottom of the inclined plane. So what I'm going to do is I'm going to think about my energy here. I'm going to start with gravitational potential energy. I'm going to end with kinetic energy and rotational kinetic energy. And so I'm going to go ahead and set up conservation of energy here. E initial plus work equals E final. I could go ahead and find the moment of inertia here, but as I know from previous problems, a lot of things are going to cancel out, so I'm not even going to worry about that. So I'm just going to think about the fact that I'm starting with gravitational potential, ending with those 2 different forms of kinetic. So it's going to be mgh equals 1/2 mv squared plus 1/2 I omega squared. 2 important substitutions I'm going to make here. The first is, I know for a solid sphere, my moment of inertia is 2/5 mr squared. And the second is that I know that velocity is just r omega, which means that my angular velocity is just v over r. I realize that I'm ultimately solving for angular speed, but things cancel out really nicely when we solve for linear speed, and once I know linear, I can easily get my angular. So I'm going to make these substitutions anyway. So we have mgh equals 1/2 mv squared plus 1/2 times 2/5 mr squared, and then that omega squared is really just this term squared, so it ends up being v squared divided by r squared. All right. A few things cancel out here. Number 1, these r squareds go away. Number 2, all my masses go away. And what I'm left with is gh, so just 9.8 times my height, which is 5.3, is equal to 1/2, and the 2's here cancel out, so 1/2 v squared plus 1/5 v squared. And so I end up getting that this becomes 7/10 v squared. And when I go ahead and solve for v, my linear velocity, I get an answer of 8.61 meters per second. Now that I have that linear velocity, it's very easy then to find my angular. I know that my angular velocity is just going to be my linear divided by my radius. So it's going to be this 8.61 divided by the radius of the sphere, which is 1.7. All right, and I get an angular speed here of 5.06 radians per second. So that ends up being this answer here, 5.1, when we round it to 2 sig figs. For this next question, we have a solid sphere rolling down an incline without slipping, has a mass of m and a radius of r, and we want to know the linear velocity of the sphere at the bottom of the incline. And so what I'm going to do is I'm going to think about conservation of energy here. I'm starting with gravitational potential, ending with two different kinds of kinetic, and I can go ahead and set up E initial plus work equals E final. And this is ultimately going to tell me what that speed at the bottom depends on. So we're starting with gravitational potential energy, so mgh. We're ending with kinetic, 1/2 mv squared, plus rotational kinetic, 1/2 I omega squared. We can plug in a few things here. We know the moment of inertia for a solid sphere is 2/5 mr squared. We know that our angular speed is just our linear speed over r, and so we can substitute in both of those quantities. So we have mgh equals 1/2 mv squared plus 1/2 times 2/5 mr squared times v over r, that quantity squared, which means that we're ultimately going to square both the v and the r. A number of things cancel out here. Those r squareds cancel out, the m's cancel out, and then this 1/2 and 2/5 really just becomes 1/5. And what we're left with is gh equals 1/2 v squared plus 1/5 v squared. And so what we end up seeing is that the mass doesn't actually matter. The radius doesn't actually matter. We can think about this on a conceptual level. Increasing the mass, all right, although it increases our final kinetic energies, it also increases how much energy we start with. And so those two effects cancel out. Increasing the radius, all right, what ends up happening with that is it increases the moment of inertia, all right. However, it also decreases the angular speed we need to be traveling at the same linear speed. And so those two effects, and we see that mathematically right here, those two effects also cancel out. So any solid sphere, regardless of its mass or radius, as long as it's a solid sphere, would reach the bottom of this incline traveling at the same speed. And so our final answer here is neither the mass nor the radius of the sphere matter. So this question is a follow-up to the previous one, so if you haven't looked at that video yet, you should, because we're going to take an idea that we learned from that video and actually use it to answer this question. So what we found from the last video was that the linear velocity does not depend on the mass or radius of the sphere. It was the same scenario, but the linear velocity doesn't depend on the mass or radius. Here's what we also know. We know that there's this connection here between linear and angular velocity, v equals r omega. So if this quantity v stays constant regardless of the mass and radius of the sphere, okay, that means that if r changes, we also need to see a change here in our angular speed to keep the linear velocity constant. And so what that ultimately means is that the angular velocity does depend on the radius of the sphere, but the linear velocity does not. Mass still doesn't have an impact because that doesn't come into play. It didn't affect linear velocity, and it's not going to affect angular either. For this problem, we have an ice skater who is spinning around in a circle, and they're changing their moment of inertia by moving their legs and one of their arms either in or out. And so we see that the ice skater is initially spinning at a speed of 5.4 revolutions per second. We want to find her new angular speed when she extends one arm and one leg outward. So this is going to be one where we're looking at conservation of angular momentum, and we're looking at it for a single object. So we're going to be thinking about our initial moment of inertia and initial angular speed compared to our final moment of inertia and final angular speed. So initially, her leg is in, and this is her moment of inertia. It's 0.8. And our angular speed is 5.4. Now, I could convert that number here, but I see that I want my angular speed in revolutions per second for my answer, and it's initially given in revolutions per second. So that means I don't actually have to worry about converting here. I can just leave it because it's on both sides of the equation. So I can say that that's equal to her final moment of inertia, which is 3.3 when she kicks her leg out, times her final angular speed. And I get an answer here of 1.31 revolutions per second. If we round it to 2 sig figs, it's just 1.3. For this problem, we have the child standing on the edge of a merry-go-round that has a radius of 2 meters. And the child is going to start running around the merry-go-round at a speed of 5 meters per second, so that's going to be the child's eventual tangential velocity once he gets up to speed here. And we want to know what the angular speed of the merry-go-round is. The merry-go-round, of course, is going to spin in the opposite direction because initially both the merry-go-round and the kid were at rest, and so in order to conserve angular momentum, the merry-go-round will begin rotating in the opposite direction. So what we're going to think about for this is conservation of angular momentum. Initially, neither the kid nor the merry-go-round is rotating, and so the initial angular momentum of the system is just 0. Afterwards, we have the angular momentum of the child plus the angular momentum of the merry-go-round. Now, for the child, we could consider the child to be a point mass, calculate the moment of inertia of that point mass, and then figure out what 5 meters per second is in angular speed. But an easy way of doing this is just doing the RP times sine of theta equation. That allows us to calculate the angular momentum using the linear momentum. For the merry-go-round, we are going to use our definition of angular momentum, which is just I omega, and that's going to be for the merry-go-round. Plugging in what we know, the radius for the child is 2. The child's momentum is just going to be their mass, 38, times their velocity, which is 5. And it is going to be sine of 90 because as they run around the edge, there's our r, and we see that's a 90-degree angle between our radius and the direction of our momentum. Plus the moment of inertia for the merry-go-round, which is 1/2 times m times r squared, okay, because it's a solid disk, times the angular speed. So we can plug in some of the things we know here. This first term becomes 380 plus 1/2 times 240 times 2 squared times our angular speed. And we end up getting an angular speed here of negative 0.791 radians per second. Now this is just negative because of how I set this up. However, for whatever reason, Mastering Physics wants the negative answer here, it looks like. So if you're having trouble with this one, put it in as a negative answer, but it should be negative 0.79 radians per second. That should work as the correct answer. For this problem here, we have two disks that are both rotating. One is rotating clockwise, like this. The other is rotating counterclockwise. What's eventually going to happen is the one disc is going to be dropped down on top of the other one, and they're going to rotate together. And we want to know their final angular speed afterwards. So I'm going to start. We know that we're going to be doing conservation of angular momentum here, so we're going to eventually be doing Li equals Lf. I'm going to start by just calculating the moments of inertia of disk A here, and also of disk B. So for both of them, the moment of inertia is going to be 1/2 mr squared because they're both disks. So for disk A, it's going to be 1/2 times its mass, which is 2, times the radius of disk A, which is 0.4 squared, and we end up getting a moment of inertia here of 0.16 kilogram meters squared for disk A. For disk B, okay, same thing, I equals 1/2 mr squared, and so for disk B, it ends up being the mass, which is 2, times the radius, which is 0.3. For both of them, I converted the centimeters here to meters, and so for disk B, I end up getting a moment of inertia here of 0.09 kilogram meters squared. Now that I have both of their moments of inertia, I can go back to setting up my conservation of angular momentum. So initially, disk A and disk B are both rotating, so I'm going to say the moment of inertia of each initially is going to be equal to the final moment of inertia of the system, and the system is going to be rotating together, so we're going to combine their moments of inertia, just like we would combine the masses of two objects that were moving together, times their final angular speed. So what I end up having is 0.16 is the moment of inertia for A. Its angular speed is 50 revolutions per second, and it's clockwise. I can leave that as 50 because my final answer here is going to be in revolutions per second, so I don't have to worry about converting. And it's negative because it's clockwise. Plus the moment of inertia for B, which is 0.09, times positive 50, that's its speed, and it's going counterclockwise, so it's going to be positive. So that's going to be equal to the total moment of inertia of our system, 0.16 plus 0.09, times our final angular speed. And we end up getting an answer here for a final angular speed of negative 14 revolutions per second. So it asks for the magnitude of their angular velocity here, so that answer is just going to be 14. But then in part B it asks for the direction, and because I got a negative answer here, and I was using the traditional sign convention where negative means clockwise, these two disks are going to be rotating clockwise after they collide in this situation.